Hello student, welcome to EPG Pathshala. In this module, today we will study about the remote sensing and GIS application in mineral resource. As you know, mineral resource is a very important resource for humankind, and from the very beginning people have hunted mineral from the different part of the globe. And in this module, we will learn how we can use different type of satellite image for mineral resource study. And in this module, we also will study about how different digital processing are required for studying this mineral resource. And then finally, we will give one case study. We will study about a case, and there we will try to find out different type of mineral exploration processes, and then we will try to see the image interpretation, how different kind of image interpretation can lead to find out different mineral resources. As you know, this for finding this mineral resource, a tedious and laborious field work is required. As in this the different part of the earth, you will find different type of minerals, and it is very difficult to to do the mineralogical mapping in the earth without going to the field. So, this remote sensing and GIS technique now helping a lot to the geologist to prepare the mineralogical map without going to field or by reducing the field work. So, today we will see how we can use different remote sensing and GIS technique to map the different area, how individual mineral we can identify using this technique. Now, the technology advancement has reached to a certain level that we can do the we can find out the rock composition, we can go for the subsurface up to shallow subsurface rock composition. So, we will learn each of these step in this module. The learning objective of this module to learn different remote sensing images used for mineral resource study. The second one is to learn digital image processing for mineral resource study. The third objective to learn how these techniques can be used for mineral exploration, and we will give a suitable example, a case study. So, in the introduction, if you can see this image, the how this mineral and human they are related, or the human is depend upon the mineral. For a particular person in his lifetime, in his or her lifetime, he requires lot of mineral resources. For example, if you look at this diagram, this figure is 2.96 million pound of minerals, metal and fuels is required for a person in his or her lifetime. So, you can see like different minerals, copper, gold, phosphate rock, coal, bauxite, iron ore, cement, natural gas, other mineral and metals, lead, petroleum, sand, gravel, silt, zinc, clay, salt. All these mineral resources are a natural resource, and human required this thing for her or his lifetime. And if you look at the figure in 2006, the requirement was 3.7 million pound per person, and in 2008 it is 3.6 million pound per person. And if you look at the in the diagram, in 2011 it has reduced to 2.96. People have realized that these mineral resources are limited natural resource. So, people have started using different kind of renewable and reuse of these mineral resources. So, we can reduce this number to the less. What happens in the developing country, people have more concern about they are limiting the use of this mineral natural resources. However, in the underdeveloped country, they still depend on this mineral in the large amount. So, in the next slide, we will see how we can use this remote sensing and GIS technique for studying these natural resources. Remote sensing and GIS techniques have been widely used in the various field of geological science. Among all, preparation of mineral resource map, exploration for the natural resource or mineral resource are important application. Mineral exploration and lithological mapping is an time consuming, laborious, and it required extensive field work. But use of remote sensing technique has drastically reduced the field work component. In the early days of remote sensing, aerial photography was extensively used by the geologist for mineral exploration. The advancement of satellite imagery in the subsequent years provided better opportunity to use remote sensing techniques for mineral exploration even in the inaccessible areas. The launch of first Earth resource satellite Landsat 1 in 1972 provided a new avenue for the geologists to interpret digital satellite image for mineral exploration. In the recent year, using high resolution multispectral satellite and airborne digital image, geologists are exploring elusive potential mineral deposits which are covered by the vegetation or quaternary deposits. If you look at the remote sensing data, this remote sensing data or information about an area or object were collected by passive or active sensor mounted in a satellite or aircraft. In the passive sensor, how it works? The passive sensor collect data using reflected or transmitted part of the electromagnetic spectrum which relay on solar illumination of the ground or natural thermal radiation of their source of energy respectively. The important sensor, the passive sensors are which are more important to the mineral resource study are Landsat multispectral scanner, that is called as MSS, Landsat thematic mapper TM utilize additional wavelengths and has superior spectral and spatial resolution compared with a MS image, and also Landsat ETM is enhanced thematic mapper. Then advanced spaceborne thermal emission and reflection radiometer, that Aster on NASA satellite Terra, and SPOT, a French commercial satellite with stereoscopic capabilities. Then the Indian remote sensing satellite IRS series combine features from both Landsat, MSS or TM sensor and SPOT HRV sensor. And the next one is your active sensor. Active sensor use their own source of energy. They emit energy and measure the intensity of energy reflected by a target. Some examples are radar that use microwaves and laser. In the European Space Agency, they have this kind of active sensor by which we can get remote sensing data for a particular area. This Landsat satellite series MSS or TM provides multispectral series having a wide applicability in geological study. Aster sensor provided higher spatial and radiometric resolution for similar part of the electromagnetic spectrum. Remote sensing data gathering system record part of the electromagnetic spectrum. Some part of the electromagnetic spectrum get observed or interrupted by the atmosphere, hence data is restricted to a particular band of the electromagnetic spectrum. Each remote sensing systems are designed to record a particular band with different spatial or temporal resolution. Hence, it decides the applicability of the data to different natural resource study. These data can be used to extract information about the lithology, rock composition, land surface structure, shallow subsurface rock types, etc. The mineral resource study the reflectance or emissivity of the mineral is used and information were extracted from the remote sensing data. When light incident the mineral or rock surface, certain wavelength of light gets observed and some are reflected depending upon the chemistry and crystal structure. Absorption of energy is mainly due to electronic processes, for example, presence of color center, charge transfer, conduction band, crystal field effect, etc., and vibration process of molecules. So, in this slide we can see the figure 1, it illustrates the whole electromagnetic spectrum, and the arrow mark in the top of this figure you can see it is indicating like it is starting from ultraviolet rays to thermal infrared region, and the visible spectrum it is elaborated in the down. You can see from violet to this near infrared range, and down it wavelengths are given in the micron size. So, in the remote sensing, in the multispectral data, what we use? We use this from ultraviolet range to this thermal infrared range, and in the figure 2 you can see some part of the electromagnetic spectrums are wholly or partly absorbed by the atmospheric gases. So, atmospheric windows where transmission occurs shown and the sensor of different satellite system that use this wavelength are indicated as a box, and electromagnetic spectrum showing the majority of the data gathering wavelengths. So, here you can see the ultraviolet region of this electromagnetic spectrum mostly get absorbed by the O3 ozone, and then if you look at the visible range, that mostly it can reach the sensor. So, that range we can get the image, and then if you look at the reflected IR, that is infrared, you can see there are different peaks and troughs. So, here like H2O, H2O will absorb certain range of your reflected IR. So, in that range, in that area we will not get any information. So, you can see 3 H2O band where it will absorb those infrared wavelengths, and if you look at the CO2 and H2O, that also will absorb, it is close to 3 micron. And then in the thermal infrared region, you can see many band it is get absorbed due to the CO2, presence of CO2, H2O or O3 in the atmosphere. And if you go to the far higher side of the infrared, there due to the presence of CO2, most of the most of the infrared it will get absorbed, and those area can be used for certain application. And here if you look at the normal color photo, what we see generally, that is restricted to the visible band. And if you look at the IR sense scanner which is fitted in the aircraft, that will take photo from the certain region of the electromagnetic spectrum. And if you look at the IR color photos, that also it takes picture from the green wavelength to the near infrared region. And if you look at the different imaging system which have been fixed into the different satellites, in case of Landsat, the multispectral scanner, there you can see the band 4, 5, 6, 7 that will collect information about a certain wavelength of the electromagnetic spectrum. If you look at the Landsat TM, it has different band, it is starting from 1, 2, 3, 4, that is close to the visible spectrum, and then in the reflected IR you have band 5 and 7, and then 6 is in the thermal infrared region. If you look at the Aster, Aster has more band, it has 1, 2, 3 that is close to your visible spectrum, and then 4 to 9, 4 and 5 to 9 that is in the reflected IR, and then if you look at the thermal IR, there we have 10 to 12 and then 13 and 14. So, these are the different region thermal different imaging system where we will take in picture or images from for different wavelength of this electromagnetic spectrum. Here in this diagram we can see how this Aster and Landsat channels are being distributed with respect to the different electromagnetic wavelength. So, if you look at the Aster image, in the Aster image you can divide into 3 different parts. One is VNIR, that is visible and near infrared radiation, in that range it will collect information. Then we have SWIR, that is short wave infrared radiation, and then we have thermal infrared radiation, that we call as TIR. And for all this band we have different spatial resolution, like for the VNIR we have 15 meter resolution, in the SWIR that is 30 meter, and in thermal that is 90 meter. And if you compare the Aster band and the Landsat, in the Landsat band you have TM 1 to 4 which will correspond to your Aster band 1 to 3, and in the SWIR, that is short wave infrared radiation, for Landsat TM you have 5 and 7, but in case of Aster you have 4 to 9. 4 is correspond to TM 5 and 5 to 9 is correspond to TM 7. Similarly, if you look at the thermal region, thermal infrared radiation, there the Landsat TM it has one band, that is TM 6, whereas for Aster you have 10 to 14. So, here you can see this wavelength of electromagnetic spectrum versus reflectance, and along with this you can see in the y axis we have reflectance from 0 to 60%. There we have plotted different material, like if you look at the water, the reflectance will be only in the visible spectrum region, and if you look at the ALOH mineral having ALOH compound, they are it will be high in the visible VNIR, and if you look at the SWIR, that is short wave infrared region, there you have the less reflectance. Similarly, you can see for the different region the behavior of this mineral will be different. So, it will help us to identify those mineral using these spectral images. If you look at the vegetation, vegetation also has different reflectance in the different region of the electromagnetic wave. And if you look at the soil, depending upon the soil composition, the behavior, the reflectance of the soil will be varying. So, we can go to the next slide. In the next slide, we will try to see how, what are the spectral range. There we saw the bands, and here it is the complete list of the spectral range we can see for the Aster as well as for the Landsat. In the Landsat you can see 1, 2, 3, 4, that is coming under VNIR, and also 8 also is coming under this visible and near infrared region, and the spectral range starting from 0.45 micron to 0.9 micron you can collect the information. And the spatial resolution is 30 meter for 1 to 4 band, and band 8 is having spatial resolution of 15. And in case of 5, Landsat band 5, that is starting from 1.55 to 1.75, that is the spectral range, and the spatial resolution is 30, and in case of band 7 it is 2.08 to 2.35, and the spatial resolution is 30. And we have another band of Landsat, that is 6, that is for the TIR region, that is thermal infrared radiation, that is 10.40 to 12.50, and it is having the high spatial resolution, that is your 60. And if you compare with the Aster, this Aster is the spectral range starts from 0.52, and in the VNIR region, visible and near infrared region, it is going up to 0.86, and this spatial resolution is 15 meter. And you can see like 1, 2, 3N, 3B, that is how we are taking the images, based on that 3N and 3B is divided. And if you come to the short wave infrared radiation, there you can see like starting from 4 to 9, you can see it has spectral range from 4.6 to 2.430, and it has a spatial resolution of 30 meter. And if you come to the TIR region, there you have band 10, 11, 12, 13 and 14, and it starts from 8.125 to 11.65, and it has the spatial resolution of 90 meter. And we will go to the next slide. In the next slide, here we have plotted different wavelength and the reflectance of different mineral. Here we can see this wavelength of electromagnetic spectrum versus reflectance of different mineral, and in the top of this diagram you can see the Aster channels, that is indicated from 1 to 9. In the top, the higher spectral resolution of Aster compared to Landsat, especially in the short wave infrared region of the electromagnetic spectrum, makes it possible to identify minerals and mineral group such as clay, carbonate, silica, iron oxides and other silicates. So, here you can see the hematite, ilmenite, kaolinite, chlorite, quartz and opal, all these minerals are plotted depending upon their reflectance with respect to their different wavelength, and this wavelength is illustrated here starting from 0.4 to 2.5. So, if you look at the hematite, it is in the pink color. You can see in the lower wavelength the reflectance of the hematite is low. As you go towards the higher wavelength, there the reflectance is high. In case of ilmenite, it has like in the lower wavelength it is low, and in between you have low reflectance at that particular wavelength. And if you look at the opals, the mostly the cryptocrystalline or microcrystalline material, or it is a glassy type. So, it has a reflectance less, that is high in the lower wavelength. As you go towards the higher wavelength, it has low reflectance. And if you look at the quartz, quartz is having very it has very different reflectance at the different wavelength. In the around 0.7 it has less reflectance, and as you increase the wavelength the reflectance is increasing, and in the towards 2.2 it has a low reflectance. And if you look at the chlorite is having higher reflectance in the short wave infrared region. And if you compare the visible part or the infrared part, you can see in the infrared part or the short wave infrared part, you can clearly see different mineral behave very differently, and this characteristics will be helpful while using this remote sensing technique to identify different minerals. And here if you look at this, it is mostly in the thermal infrared region, that is in the higher wavelength side. You can see the Aster bands are illustrated here as a 10, 11, 12, 13 and 14, and different mineral like you can see quartz, hematite, ilmenite, kaolinite and chlorides are plotted with respect to TIR, and here you can see quartz, kaolinite and chloride. These three you can easily identify in this region, but only in the 10 to 12 channel region, area. In the 13 and 14 they are not very distinct, but still we can use this band to identify different minerals. And this information has been taken from is a library spectra. This is from Johns Hopkins University. It is superimposed on the Aster data band interval in the TIR region. So, here if you look at this spectrum, Aster TIR spectrum of different rock types, as we know different rocks are composed of different minerals. So, depending upon the mineral composition, this rock type, the behavior or the characteristic of this different rock, it will differ. And here you can see different rock type like lithogranite, granodiorite, quartzomongirite, granodiorite, diorite, anorthosites. These are the different rocks are plotted against the emissivity. This in the thermal infrared region we call it as emissivity, we use the terminology emissivity, and for the lower one we used as a reflectance. Here you can see in the 10 to 12 band and in the 13 to 14 band how these different rock types are showing different kind of spectra. So, if you see the arrow mark, this arrow mark indicating how the emissivity of the rock change with respect to the silica content. It is shifting of minimum to the shorter wavelength as silica content increases. In case of lithogranite, the silica SiO2 content is much higher. It is more than, it is close to 70.8. If you will compare with the anorthosite is having 49.7. So, the silica SiO2 percentage is decreasing as we come from top to bottom, and with respect to that you can see the shift of minima in this band, it is moving towards higher wavelength, or in the vice versa. As we increase the SiO2 content, this the minima is shifting towards the lower wavelength side. So, this is another characteristic by which we can identify rock and we can get information about the rock composition. And this silica content, that we can also compare with the quartz percentage. Quartz is a mineral, and you can see in case of lithogranite, granodiorite or quartzmonzonite, the silica the quartz percentage is quite high compared to the diorite or anorthosite. So, in one way we can identify the rock, we can get the rock composition as well as the mineralogical composition also will get information about the mineralogical composition. So, till now we are discussing about the Landsat TM Landsat MS or Aster image. These are the multispectral images. In these images, what happens, several to tens of bands are present. So, we can get information for this individual spectral range, and from that we can get information about the mineralogical or rock composition. If you look at the hyperspectral, this is the due to the advancement in the technology, now we are collecting information based on the hyperspectral range, and in the hyperspectral you can see like hundreds of narrow bands are present. So, we will get more detailed information about the particular mineral and rock. In this hyperspectral images, what happens, the acquisition of hyperspectral images in hundreds of registered continuous spectral band, such that each picture element or pixel of an image will provide a complete reflectance spectrum. This image have many narrow band with 10 to 15 nanometer spectral resolution, which is very useful for discrimination study to identify different mineral and rock. And this hyperspectral images is like Hyperion or Olli. These are the different type of hyperspectral image now people are using to get information about the mineral and rock composition. And this it required more complicated image processing. We will be discussing the image processing in our subsequent slides, but here if you look at this figure, you can compare like multispectral and hyperspectral image. So, here like in the left corner you can see the electromagnetic spectrum is divided into different area. For example, like BGR, it is the part of your visible range, that is blue, green and red, and then you have NIR, near infrared region, short wave infrared region, and medium wave infrared region, that is mostly thermal region, and below that you have this multispectral bands. So, here you have several to tens of bands, and we will get, for example, if you take kaolinite of Landsat TM, and if you are comparing with the hyperspectral image, then you can see in the Landsat TM it is giving a very simple curve, but in the hyperspectral we can see for narrow band the reflectance is different, so it is less. So, we can very clearly see those change in the different mineral, and it will be helpful to discriminate different mineral. In the left side down you can see the hematite, ilmenite, kaolinite, chlorite, quartz, opal, all these things are plotted. This diagram already we have discussed in our previous slides. So, here I have kept only to compare how this hyperspectral and multispectral you can use for the mineral resource study. Go to the next. So, here you can see how exactly this hyperspectral images are we acquire these images. So, hyperspectral sensor, it will continuously collect information for different band. So, each of the pixel, it will have, depending upon the pixel size, here it is 30 into 30 pixel contains a continuous spectrum used to identify material by their reflectance or emissivity, and you can see the continuously we are for a particular mineral or rock, we are continuously getting information for each of the wavelength. And here in the diagram, the stacking, you can see this stacking is nothing but the information about the different wavelength. Depending upon the spectral resolution, you can have multiple layers of this information, and that depending upon your requirement, you can extract those information from these images. And here, depending upon the swath size or the spectral dimension or the pixel size, you can use different multispectral hyperspectral images for different kind of mineral mapping or the lithological mapping, or to know the surface composition. So, if you look at the images, the satellite images, what is the characteristic of the images? Prior to the image processing, for getting any information about the mineral or rock or the lithology, we should do some we should know about the image. So, each of this image, it has numbers of spectral band, it will have a particular swath, it will have successive path overlap, temporal resolution, etc. So, we should know about those images before processing. so that we can use this information while interpreting the image for this mineral resource mapping. So, another important parameter we should know, that is your pixel parameter. The digital image consists of discrete picture elements or pixels. Each pixel associated with a number that signifies the average radiance or brightness, which represents reflected radiance from surface and radiation scattered by the atmosphere. Both information will be present. Each of this pixel parameter is grouped as an 8-bit, that is in the byte of information, with each bit used to indicate ascending power of 2 from 2 to the power 0 to 2 to the power 7. So, this information we can use to extract the get the information. The instantaneous field of view IFOV is the distance between consecutive measurement of pixel radiance, which is also called as pixel size. For example, if you look at the Landsat MS, the pixel size is 79 meter into 79 meter, but in case of TM and Aster, it has 30 meter into 30 meter pixel size, and for some band you have even 15 meter pixel size, 15 into 15. And then another one is image parameter. In the image parameter, number of pixel per scene decides the resolution of the image. In the multispectral image, same scene image simultaneously in several spectral band. The image intensity level histogram is a useful indicator of image quality, which describes the statistical distribution of the intensity level, and this image parameter we can use for the interpretation. Before getting any information from the image, we have to go for the digital image processing. For mineral resource study, important function of digital image processing are: first one is image restoration, second one is image enhancement, third one is information extraction. And each of these functions, it has different steps, that is again depending upon our requirement and depending upon the type of image. However, this in the image restoration is the process images are corrected for inherent defects incorporated during data collection. So, the important corrections are like correction for the lost data, that sometime what happens in the image, we can see some lines are missing or pixels are bad. So, that correction we have to do, and different methods are there to do the correction. The second one is atmospheric noise correction. As you know, these images, while collecting this capturing the images, the radiations are going from the sun, it is going down and it is getting reflected back from the object. So, it is traveling the atmosphere. So, the noise produced by the atmosphere, that has to be corrected before doing the any further study of this satellite image. Then the third one is geometry correction. Geometry correction is an important correction, because the earth rotates during the time it takes the satellite to scan its swath, resulting in the skewed image. So, geometry correction is required, as images are needed to be integrated with geophysical, topographical, geochemical, and other map based data. So, geometry corrections are very much important before going for further processing. Second one is image enhancement. It transfers the original data to improve the information content. So, important ones are, the first one is your contrast enhancement. Contrast stretch is, it is a simple linear transformation, is routinely used to increase the contrast of the displayed image by expanding the original gray level range to fill the dynamic range of the display device. So, depending upon the type of image, we have to first change the we have to enhance the contrast to get more information from the image. And then the second one is spatial filtering. It is used to enhance the linear surface feature such as fracture, fault, joint, etc., which is very essential in while doing the geological study. Then density slicing. In the density slicing, it transfers the continuous gray tone range into a series of density intervals, which we call as a slice, with a specific digital range. Each slice may be given a separate color or line printer symbols. Then the fourth one is false color composite image. During this image enhancement, we can also produce this false color composite image, or we also called FCC images. as we know, this multispectral false color image, it is generated by combining different spectral band and assigning a different color to each band. It increases the amount of information available for interpretation. While collecting this information, what happens? We are collecting information for each of the spectral range. So, during this process what we do? We combine different spectral band and we assign each band a different color. So, we are creating a we are creating a different color composite image. So, we call it as a false color composite image, and it will help us to gather more information from this image. Next important aspect is how to get information from the image. So, if you look at the image interpretation, in the image interpretation there are different things, like for example, image elements are there, terrain elements are there, spectral signature of rock. Based on this we can interpret those image to get valuable information about the geology of that particular area. So, if you look at the image elements, what are the things are coming under image element? That is tone or color, texture, pattern, shape, size, shadow, site and association. Here in the image element, for example, tone and color, in the what kind of color, the gray scale, that will, from that also we will get information about that particular area. Texture, that is change in the tone, that also we can check here. Pattern, shape, that particular object shape or size, that also will give information about that geology of that area, and we can use this information while preparing the lithological map or while preparing the mineral resources. Then the terrain element, for example, drainage pattern, drainage density, topography, landform and erosion status. This here in the terrain element, drainage pattern or drainage density, that is with different type of drainage they develop over different type of rock. So, from this particular interpretation, what we used to get, we get a bulk idea about a particular lithology present in that particular area. And then the spectral signature of rock. So, using image element and terrain element, we will get a broad idea about that particular rock or particular lithology or particular geology of that particular area, but we will not get more information about the chemical composition or mineralogical information. But if you analyze the spectral signature of rock or the mineral, then this thing will help us to go for the mineral exploration. You can to prepare the mineral resource map. So, here if you look at the drainage pattern, for as we have discussed before, the terrain element, in the drainage pattern, based on the different drainage type, you can get different information about that particular area. For example, if you have a dendritic drainage pattern, so the geological significance of this particular drainage is like this kind of drainage will develop in a region of rock homogeneity, shows lack of structural control, indicates horizontal to subhorizontal beddings and gentle regional slope. For example, shale or granitic gneissic rock, in those kind of area dendritic drainage pattern will develop. So, based on this drainage pattern, we will get information about the lithology rock type. Rectangular drainage pattern, so just it will show the structural control, develops along the joints, faulty intersecting of right angle. So, for example, if you have a sandstone area and it is having a structural control, you will get those kind of drainage pattern. If you are getting trellis, so it shows a structural control, again develops in areas having parallel fracture or fault, tilted interbed sedimentary rocks and difference in rock resistance, and also we will get release in the folded sedimentary sequence. So, here we will get information about overall rock type based on this drainage pattern. If you have parallel drainage pattern, this parallel drainage pattern will develop due to the pronounced regional slope or it in a area having elongated geomorphic features such as homoclinal ridges or quartzitic rock. So, some broad some idea we will get from drainage pattern. If you have radial and drainage one, then you are going to get different information. For example, radial, if you have radial drainage pattern, pattern, then it will be associated with dome, doubly plunging fold, volcanic mounts. In those area you will get this radial drainage pattern. Deranged one you are going to get in the limestone, or in indicates the limestone in the humid climatic area. So, what we learned from this particular slide is, based on the different drainage pattern, you will get some information about the lithology or the rock type of that particular area. For getting more detail about the mineralogy, to know about the rock composition, we required some more processing, digital processing, so that we can get more information about that particular rock, or we can clearly tell that what kind of mineral is present in that particular area. So, geological information can be extracted from the image by various methods, such as band ratio, multispectral classification, principal component analysis, etc. So, here what happens, if you take the Landsat TM or Aster image, there you have different band, and each band will be collecting information for that particular rock. So, here what we do, we use different band, and we apply various method to get information out of that, which will help us to identify the mineral and the rock composition. So, let us start with the band ratio. In case of band ratio, what we do, dividing a gray level of pixel in one band by another band. This ratio help to identify the ferruginous and limonite capping, which also called as a Gaussian. Soils and exposed rock rich in the iron oxide and hydroxides observe wavelength of 0.55 micron and cause red coloration. And sometime what happens, when these minerals mixed with other mineral, it masks the coloration. Hence, it is important to discriminate different minerals. So, a ratio of MSS band 4 over band 5 will enhance the small contribution of the iron mineral. So, you can discriminate those and you can identify the mineral. Similarly, a ratio of MSS band 6 over 7 will discriminate areas of limonite alteration. And by ratioing TM band mineralogical spectral, the characteristic related to the alteration can be determined and detected. Aster has even finer spectral band, which gives enhanced alteration discrimination. Using this ratio, we can also detect the alteration zone. This identification of alteration zone is very important when you are studying the mineral exploration. Many times what happens, different type of mineral get enriched near to the alteration zone. So, it is helpful to identify the alteration zone for the mineral exploration. The Landsat TM scanner has two critical. A ratio band of 5 to 7 is used to identify hydrothermally altered rocks. So, this is also helpful for making the mineral exploration. And a complete list of this different band ratio Aster used for identification of various mineral is given in the next slide. In the next table we can see here. So, here you can see different mineral is grouped under different category, and what are the band ratio we are using to get this information. For example, if you look at the iron bearing minerals, if you have ferric iron, so for Aster band we can use like 2 by m 2 by 1, and for ferrous iron you can go for 5 by 3 plus 1 by 2, and if you look at the laterite, there you can go for 4 by 5. For Gaussian is a cap rock which can indicate what kind of mineral deposit present below that particular area. For Gaussian identification we can use 4 by 2. If you have ferrous silicate, for example biotite, chlorite, amphibole, we can go for 5 by 4, that is band 5 by band 4. If you have ferric oxide, then you can go for 4 by 3. If you have carbonate or mafic minerals, then you can go for different band ratio. For example, carbonate, chloride, epidot, there what you can do, you can add 7 and 9, and then you can divide, you can take ratio with respect to 8. And if you have epidot, chloride and amphibole, you can combine this 6 plus 9 divided by 7.8. Similarly, you can see for amphibole with MgOH functional group, if you have dolomite, you have carbonates. So, different band ratio you can use. That is again depend upon the our requirement, we can go for different band ratio and we can get information about this mineral, the presence of this mineral. If you look at the silicate, there are different silicate minerals are there, for example, cerisite, muscovite, illite, smectite. These things for identification of these minerals, you can go for 5 plus 7 divided by 6. So, for individual, like if you have muscovite, kaolinite specifically you want to identify, then you can go for the 7 by 6, 7 by 5 respectively. And if you have silica rich minerals, for example, quartz rich rocks, then you can go for the TIR bands like for 14 by 12. If you have simple silica, then you can go for 11 by 10 or 12. If you have other mineral like garnet, clinopyroxene, epidot, chlorite, you can use 12 by 13. For the different type of silica, if you have silica, you can go for different type of band ratio, and you can compare. And other than this mineral, you can also identify, like for the vegetation or NDVI, you can go for different kind of ratio. So, here you can see you can go for the different enhancement. Here for the visible range, you can see like you can use for red, green and blue enhancement. You can go for different kind of ratio. Here also you can see in the first column, it has given for the different type, like for example, for identification clay, amphibole laterite or Gaussian alteration and host rock. You can go for this different kind of band combination or the ratio. And for example, for the if you are planning for a discrimination for mapping, then you can go for different band ratio for the different range. And discrimination 1, 2, you can go for 4 by 7, 4 by 7 for the red. For the green, you have to use a different band ratio. For silica, again you can go for this higher 14 by 12. So, by using this, we can enhance this picture and we will get enhance this image, and we will get information about from that particular image. So, now the another method that we called as a spectral angle mapper, that is SAM. This SM or SAM determines the similarity between an image spectrum representing an unknown material and a reference spectrum representing a known material by computing the spectral angle between them, treating them as a vector in n dimensional spectrum spectral space, where n is the number of bands. This method is independent of illumination condition, that is topographic or shading, and widely used for the spectral matching. So, here in this picture you can see you have two different band 1 and band 2, and you have two spectrum. One you have the reference spectrum, that material B, and the image spectrum is material A. So, one is your unknown, that is your image spectrum, and known one is your reference spectrum. So, between these two, what is the spectral angle? Based on this angle, you can also get information about the lithology, you can get information about the rock type. So, what happens here? How we are getting information from this particular exercise? That is, if you have a smaller angle, that will represent closer match to the reference spectrum. If your pixel farther away than a specified maximum angle threshold in radians, that is will be not classified. A vector from the origin through each point describe the position of each respective spectrum under all possible illumination condition. SAM is insensitive to the illumination and albedo effect, which means that all possible illumination are treated equally. And then poorly illuminated pixel fall closer to the origin of the scattered plot, and you can see from this this exercise, the color of the material is defined by the direction of its unit vector, and the angle between the vector is same regardless of their length. So, using this exercise, using this method, we can get information about that particular area. Another one is the multispectral classification. In this process, a symbol or color is given to a pixel or a small group of pixel which have a high probability of representing the same kind of surface material, for example, alteration. Multispectral classification is particularly useful for a large area or a region covered by dense vegetation, as a difference in the vegetation reflect the underlying geology. So, using this classification scheme, we can identify, and this process is mainly done by the digitally this process is carried out. The fourth one is the important one is principal component analysis. It is used to enhance or distinguish lithological difference, because the spectral difference between rock types may be more apparent in a principal component image than in the single band. The reflectance in the different band in MSS, TM or Aster image have a high degree of correlation. Principal component analysis is a commonly used method to improve the spread of the data by redistributing them about another set of axes. This effectively exaggerate difference in the data. So, it will be helpful to identify different mineral or the rock composition. So, here before going to the case study, let us see how we are going to prepare this lithological map using a satellite image. So, first thing is, first we should have a geocoded multispectral image, and also we require a geological map or other published geological some background information about that area. If you look at the geocoded multispectral image, from that what we have to do? We have to go for the image enhancement, as we have discussed. In the image enhancement, we are going to prepare suitable FCC, that is false composite color map, then band ratioing, then FCC from band ratio, application of different stretching techniques, that is to these are the technique required for the image enhancement. Once the image enhancement is done, then we will go for the image interpretation. In the image interpretation, to delineate lithology with the help of different photo interpretation key, what we have discussed under the image element and terrain elements. For example, tone, texture, color of image and geological keys such as drainage pattern, weathering pattern, structural disposition, etc. Using that, we will get first hand information about the lithology, and then we will go for the demarcation and updation of different rock types and their boundaries and preparation of final lithological map. And to this one, what we are going to do, whatever background information we have about that particular area, that from that also we can go for the image interpretation, and that will help us to prepare the lithological map. And using the field survey, we can validate the result obtaining from the satellite data and geological map. And once this part is done, then we can go for the final preparation of the lithological map. And once that is done, edge matching with the adjacent map produced from the satellite data to maintain the spatial continuity of the rock types, that we will carry out. In this way, this is the flow chart where we can you can see that the steps for preparation or updation of lithological map from the satellite image. And here this is another flow chart where we can see how to use this remote sensing data to get different geoscientific information, and which is more important to the mineral exploration. This flow chart and the previous flow chart has been taken from remote sensing application, that is 2010 published by NRC ISRO Hyderabad. So, here you can see before starting this, we should have existing thematic map or the geological map of that particular area. We should have remote sensing image, whether it is a Landsat, IRS image, Aster, RadarSat or Hyperspectral. The Hyperspectral is a hyperspectral image, and you should have some field data. So, thematic geological map or existing thematic map, that we have to go for the digitization. Similarly, field data also will go for the digitization, and the remote sensing image will go for the georeferencing using DM or the topographic map. And this if you look at the thematic map, after digitization we have to prepare the different vector layers, and field data after digitization will go for the geostatistical estimation, the kriging, variographic analysis, that will do, and then we will prepare grid layers, different layers. And from the remote sensing image, what will after georeferencing will go for the image processing, that is geometric correction, orthorectification, whatever atmospheric correction, that we have to complete, and then we will prepare the grid layers. And at the same time, if you have other data, for example, geochemical data you have or geophysical data you have already, then from that you have to go for the interpolation. If you have data from a small area, you can go for the interpolation and you can go for the grid layer. If you have geophysical data, then go to the grid layer. Once you have grid layer and vector layer, using these two you can prepare the GIS database. Once you have the GIS database, from the GIS database you can prepare different thematic maps and you can have different layer. For example, you can have the geological layer. What are the layers under geological thematic map you can prepare? That is lithological layer, structural layer, hydrothermal alteration layer, geomorphological layers, mineral occurrence layers you can prepare. Geophysical layers you can also prepare magnetometric, gravimetric, aeromagnetometric, that you can prepare. This thematic map you can prepare. Then for the geochemistry thematic map you can prepare, and other thematic map like topography, DM, field radiometry, drainage network, etc. These are the different layers you can prepare using this GIS database. This GIS database that will further go for the data processing, where we can classify those things, those information like buffering, reclassification, selecting contact, sorting out different features, and then we can integrate. Once we do the data processing, then we can go for the integration modeling. Once the integration modeling is done, then we will go to the geognostic variable selection. That is, for example, we are going to find out a particular mineral deposit. So, whatever area we have selected, how far it is from the intrusive body or the proximity to intrusive body, lineament, hydrothermal alteration, etc. Or we can go for the lithological contact, we can go for the we can find out the geophysical anomaly or geochemical anomaly. Those information we can select, we can categorize those information, then we can go for, we can prepare the different class map source we can develop. Then we, whatever variable parameters we have, or depending upon the class, we can give weightage to this different variable. There are different method, you can give you can assign Fusi weight to this different variable. Then the next step will be combining maps, example with the Fusi logical operator like or gamma with the mineral potential index or a mineral potential score, and then from this one we can go for mineral favorability map, mineral potential index map, mineral potential map, or the mineral potential score map, that we can prepare. And finally, we have to go for the validation. In this way, you can start the mineral exploration work for a particular area using remote sensing data and images. So, we will go for a case study. This case study actually has been taken from this Landsat et al. 2014, the processing of multispectral Aster data for mapping alteration mineral zone aid for the uranium exploration in an area where you have the granitic rock, that is in the Egypt. So, objective of this paper was, author's objective was to map the alteration mineralization and a zone as a pathfinder for uranium mineralization with a Emiscat and Eleridia younger granite, that is in the central eastern desert Egypt, that may assist in developing a uranium exploration program using Aster imagery. Why I have chosen this paper? Here we can see how in that area you will see already people are having this uranium exploratory they have developed, and now using this Aster image, how we can complement those, or how we can find out what are the mineral, or how we can use this alteration zone to do the mineral exploration of that particular area. So, in this paper, what are the process the author has done? The Aster image he has taken, and the initial processing like orthorectification using SRTM topographic data he has done, then converting pixel radiance at the sensor into the reflectance at the surface data using first line of sight atmospheric analysis of spectral hypercubes, that flash module of NV software, and thermal atmospheric correction of Aster TIR emittance band were applied, and then the feature oriented principal component selection and the spectral angle mapper are the main image processing technique has been used here to get information about the mineral exploration. So, if you look at this diagram, here you can see the geological map. So, here you can the color indicating the different rock type present in this particular area. We for this particular area we have the geological map. You can see the red color one, cyanogranite. This cyanogranite, the probability of mineralization is in the cyanogranite. So, you can see one yellow color symbol, which is the uranium exploratory mine. It is present in this. You can see this red color area, where in the top part of the red color area, in the northeast corner of this figure, you have one yellow color mark, which is a uranium exploratory mine, and in the northwest and in southeast corner you can see 2 points where you have the exploratory mine. Now, we will look for this particular red area where we can find this uranium mineralization, how this remote sensing technique will helpful go for this mineral exploration. This is a false color composite image of the Aster band 9, 8 and 1, that is for the red, green and for the blue, discriminates the different rock units. Here you can see the gray color one, that you can clearly see the previous diagram. Here you can see the red color part, they are in the false FCC. You can see they are clearly distinct from the other rock. So, our focus is in this area, and we are going to see the different processes. So, for first one is your feature oriented principal component analysis. You can see for the identification of different mineral, for example, kaolinite, chlorite, illite, hematite and quartz, different band they have chosen, high and low. For example, band 3, 7, that is coming under the visible and near infrared to short wave infrared region. So, that they have used, and also they have used thermal infrared radiance. So, different band they have used for the principal component selection. And then you can see in the bottom one different band like band 3, band 6, band 7, band 9, they have used for analyzing this principal component analysis, PC1, PC2, PC3, PC4. So, you can see Asian vector value for selected VNIR and SWIR Aster band for the kaolinite is given here. Similar, we are not worried here. I am not discussing the what value they are going to get. The more important thing is what is the process. So, this is one example I have given. So, similarly, this is for the VNIR and SWIR, and similarly for TIR also you can calculate separately this principal PC1, PC2, PC4. Each of this mineral you can do this principal component analysis and will get the information about this different mineral. You can see here band DN threshold that they have calculated from the mean plus 2 into standard deviation of that particular one, and this information they have used to get the mineral deposits. So, here you can see this image based on this principal component analysis PC3, you get resulted PC3 kaolinite image using FPCCS technique for the input of VNIR and SWIR bands applied on the cyanogranite. Magenta color pixel that is representing kaolinite anomaly. So, DN value you can see that DN value is given in the diagrams, picture A and B both are given here. One is for the visible near infrared and short wave infrared band. The picture B, it is for the thermal emissivity band. So, here you can see how the anomaly of this kaolinite. If you look at this image, so green color DN value, here the chlorite anomaly you can see both in the visible near infrared and short wave infrared bands as well as in the thermal emissivity band, and you can see the anomaly, chlorite anomaly, and you can find out those anomaly. And in this picture the same method has been applied. You can see the illite and the hematite. This illite is in the blue color, you can see in the left side picture, PC4 illite images that you can see here, and the right side picture is your hematite anomaly. So, hematite is red color is given in the red color. So, here for the quartz anomaly. In the cyan color is given for the quartz. So, you can see here from the quartz anomaly you can clearly distinguish. So, what we have learned, what we have done here using principal component analysis, our target area find out this anomaly, the mineral anomaly, and we can prepare map. And the second method was your SM. So, matching of maximum angle radians using SM classification of Aster bands. So, here you can see for the different end member, here we have chosen, that is with respect to reference mineral, we have to compare the reference and unknown mineral. So, here the end members are sericite, chlorite, hematite, illite, kaolinite and quartz, and for the different band you have the different angles. The maximum angle in radians you can see for VNIR and SWIR it is listed here, and for TIR it is listed separately. And if you look at the image is being generated using this SAM, the SAM angle you can see it is 0.150 for the sericite and color is cyan color, and for both image you can see that is compared that is for the sericite, for the TIR and for a visible near infrared region we can clearly demarcate this sericite. Similarly, in the illite also, for illite we have calculated separately, we have done the SAM classification, end member is your illite, and based on that we have prepared this image. Here the spectral library was applied, and in this diagram you can see the quartz. SAM classification, end member is quartz. So, it's resampled spectral library applied on this particular cyanogranite, and in the right side image is your TIR band. So, same way you can see very clearly, we can see this different mineral anomaly. So, what we have learned, we have used two method here to identify this mineral, the presence of this anomaly of these minerals, and concluding remark of this case study is from this FPCS and SAM image the resulted alteration mineral map, especially the silica, which is nearly coincide with the radioactive anomalies and could be used as a pathfinder for new uranium exploration site within the study area. So, we have taken many mineral, out of that quartz, the presence, the anomaly map what we have prepared, alteration mineral map what we have prepared based on the SAM and FPCS. So, that is matching with the radioactive anomaly from that particular area. So, based on this particular mineral, this mineral can be act as a pathfinder for the new mineral exploration of that particular area. So, that is how we can use this technique to identify different mineralization. And if you look at this alteration mineral, there are different type of alteration minerals that is identifiable by the short wave infrared spectroscopy, and using these alteration mineral you can go for the mineral exploration. For example, if you look at the clay, in the clay different type of clay minerals are present. For example, kaolinite, dictite, halloysite, pyrophyllite, illite, smectite, montmorillonite. These are the different clay mineral you are going to get in the alteration zone, and this will be a useful parameter to identify different mineral deposits. And mica, if you look at the mica, white mica you have illite, phengite, muscovite, paragonite, biotite, phlogopite, pyrophyllite, etc. that also coming under this mica group that you can use. Chloride, you have different type of chlorides, you have different type of phyllosilicates, you have different type of amphiboles, that what we are going to get in the alteration zone, and it will be useful. So, using this technique we can identify this mineral, and based on this presence of this mineral can be a pathfinder to other mineral deposit. So, if you look at the tourmaline, Fe tourmaline you have, other normal tourmaline you have sulfates, you have alunite, jarosite, gypsum, these are the different sulfate minerals. You can also have different major absorptions, like for example, ALOH, that is clay and mica, you are going to get FuOH or MgOH. These things are present in different mineral. So, based on this information also you can identify this mineral, and you can also prepare the mineral resource map of a particular area. If you look at the Indian organization who actively use this remote sensing and GIS in mineral exploration, for if you look at the GSI, that is Geological Survey of India, they routinely use this remote sensing for lithological mapping and mineral identification, mineral resource map. AMD, Atomic Mineral Directorate for Exploration and Research. It is it is coming under Department of Atomic Energy. ONGC, they also use this remote sensing and GIS for various purpose. ONGC is Oil and Natural Gas Corporation Limited, MECL, Mineral Exploration Corporation Limited, India, and NRC, this National Remote Sensing Center is a ISRO organization of ISRO, and they routinely use this remote sensing and GIS technique for the mineral exploration, for mineral resource, for preparing mineral resource map, for lithological mapping. In this module, we have learned about the different type of remote sensing images, and we have also learned what are the different technique, how we can use this image to get information about different mineral resources, how we can use these different images to prepare the lithological map or mineral resource map. And also we have discussed about one case study, and we know this importance of the mineral resource to the mankind, and it is very important to prepare this mineralogical or lithological map very efficiently and without going for a laborious field work. So, this remote sensing and GIS technique is very helpful to prepare to make this lithological map and mineral resource map. So, this module will help us, it will give you a first hand experience, first hand learning to how we can use this remote sensing and GIS to prepare a lithological map and mineralization. And it is very important, this technique is very important for the mineral exploration purpose. At many many location it is very inaccessible and it is difficult to go for the field work, and it will be time consuming and cost effective. So, applying this remote sensing and GIS, we can go for a detailed mineralogical mapping of that particular area, we can go for the mineral exploration, also we can go for the mineral or rock composition of subsurface that where it is covered by the vegetation or the quaternary deposits. So, I hope you have learned something from this particular model about the application of remote sensing and GIS in mineral resource study. Thank you.